This is an analysis of problem G called Metal Processing Plant from the ICPC World Finals 2014. This is a kind of clusterization problem. So the metal processing plant gets shipments from different places, and some of them are very similar to each other and some of them are really different. And we need to separate the shipments in two groups or two clusters, A and B, so that the shipments in the same cluster are similar to each other. And to make that mathematically rigorous, we're given the similarity between each pair of shipments as a distance function. d of ij is measured between each pair of shipments I and j. And distance between similar shipments is small, and for different shipments it can be bigger. Then we define the disparity of set S, d of S, as the maximum distance between each pair of shipments inside the set. And we need to minimize the total disparity of our division into two groups, d of A plus d of B. So basically we take each shipment X and we put X either into A or into B, and then when we're finished we compute the disparities of sets A and B and sum them up, and then we want to minimize this sum. This is actually one of the hardest problems of these World Finals. And the solution goes like that. First, let us assume that the disparity of set A is less than or equal to the disparity of set B. This can be done without loss of generality, because if it is not true, we can just swap A and B. To solve that, we first iterate through all possible values dB of the disparity of set B, and all those values are basically all the values of the distance function between each pair of shipments. When we fix dB, we can make binary search over all possible values of the disparity of set A. Why can we make a binary search? Because if some value of the disparity of set A is possible, then bigger values are also possible, and we need to find the smallest possible value of dA given the value of dB. And so if we have a procedure to check whether it is possible to construct set A with the disparity less than or equal to dA and set B with disparity less than or equal to dB, then we can make this all work. We basically iterate through all values of dB, make a binary search through all values of dA, and then check whether it is possible to have this pair of dA and dB, and then we find the smallest possible sum of dA plus dB. So how to check whether this pair of dA and dB is possible or not? Basically, we should check whether for each pair of shipments X and Y it is possible to somehow distribute them into sets A and B. And that depends on the distance between X and Y. If the distance between X and Y is less or equal to dA, then this pair is easy. It doesn't matter whether to place X and Y into A or into B or into different sets, because anyway pair XY won't break our conditions, because the distance between them is too small. The next case is when the distance between X and Y is already more than dA but still less than or equal to dB. In that case, at least one of shipments X and Y must be in B, because if both of them are in set A, then the disparity of set A will be at least d of xy, which is bigger than dA, and that breaks our conditions. But if one of X and Y is in B, then it's still okay, because the distance between them is less than the restriction on the disparity of B. Then, if the distance between X and Y is even more than dB, then X and Y cannot be in the same cluster, because if they are in A, then the disparity of A is too big. If they are both in B, the disparity of B will be too big. So one of them should be in A and another one should be in B. If these conditions are true for each pair X, Y, then we can construct sets A and B. Basically, that's what we have to check. These conditions for each pair X, Y. And that can be reduced to two SAT problems which is well known, and I think many of the participants of the World Finals can code that up pretty quickly. So for each shipment X, let's make a Boolean variable bx, which means X is in B. If it is true, then X is in the set B, otherwise X is in the set A, because X should be either in A or in B. We must divide all shipments into those two groups. So if the distance between X and Y is less than dA, then this pair adds no conditions to the formula we are building. If d of xy is more than dA but less than or equal to dB, then we will add condition bx or by, meaning that at least one of the shipments X and Y should be in the set B, as we saw on the previous slide. And finally, if d of xy is more than dB, we add the condition bx or by and not bx or not by, meaning that one of the shipments X and Y should be in B and another shouldn't be in B and should be in A. And then we make a conjunction of all those conditions for all pairs X and Y and check whether there are values for all those values bx and by such that the formula is true. That is basically a 2 SAT satisfiability problem. So we can solve that. Let us estimate the complexity of this solution. First, we have n squared variance for dB in the outer loop, because there are n squared distances between different pairs of shipments. Then we have inner loop with the binary search, and in the binary search we have n squared variance, but as it is binary search, we only have to do logarithmic number of iterations to finish with it. So it's log n iterations of the binary search. And then inside the binary search we need to check whether it is possible or not to have such pair of values dA and dB, and it will take n squared time, because there will be n squared pairs of shipments X and Y, which will generate n squared conditions, and the complexity of 2SAT depends linearly on the number of conditions. So overall, this will be a solution which works in the time n to the power 4 multiplied by log n. This is actually too slow to pass in the time limit in these World Finals. As it is not complex enough, the authors wanted us to optimize this solution even more. So, how can we optimize it? We can reduce the number of variants for dB using a maximum spanning tree, which is surprising. So, how to do that? We want to construct set V of all possible values of dB. Previously I told you that any distance between shipments X and Y could be a possible value for dB, but actually that's not true, because dB is the maximum distance between all pairs of shipments in the same cluster, and so it actually cannot be any value of distance between pairs of shipments. And actually there is only a linear number of different variants that can be the disparity of set B. So to construct that linear number of variants, we first build the maximum spanning tree on the graph of shipments, and the graph is built using the distance function. Basically there is an edge between each pair of shipments, and the weight of that edge is the distance between that pair of shipments. And then we build the maximum spanning tree, which is basically the same as minimum spanning tree, but with maximum instead of minimum. And then we add all of the edges of this tree to the set V of possible values of dB. But that's not enough yet. We also need to color the tree into two colors, so that there are no two nodes which are neighbors and have the same color, the basic two coloring problem. And then we will add the maximum edge between nodes of the same color to the set V, and then we can prove that this is a sufficient set, so that any value for dB is contained among set V. So then set V contains all necessary values, and the size of the set V is linear, because there is n-1 edges in the maximum spanning tree, and we also added one edge which is maximum age between nodes of the same color. So the size of set V is n. And now the outer loop is n instead of n squared, and the whole solution works in the time n to the power of 3 multiplied by log n, which is sufficient to pass the time limit. Actually, during the contest, some team passed this problem, but they had a little bit different solution. They had solutions that worked in time n to the power of 4, and it turned out to be also sufficient to pass the time limit. So instead of using the surprising method with the maximum spanning tree, they eliminated the binary search. So when we search for dA, instead of looking for all possible values of dA in the binary search, we can start looking for dA from 0 and go up and make a linear search. But also search for dB not in a random order, but start from the maximum edge and go down. And then when we go from some value of dB to smaller value of dB, we can only increase the value for dA, because it cannot go down. If some value of dA was possible for smaller value of dB, it will be also possible for bigger value of dB. So when dB goes down, dA must go up. And when dA and dB meet, we stop our search. So there is no need to decrease dA after decreasing dB in the outer loop. And so overall we will make only n squared iterations in both the outer loop and the inner loop, because we make n squared iteration at most in the outer loop, and in the inner loop the dA can go only from the smallest edge to the biggest edge without decreasing ever, and so it will make at most n squared steps overall. And then we don't multiply those, we just add them up, because dB goes only down and dA goes only up. And thus there are only n squared variants for the pair dA and dB instead of n squared log n when we were using binary search. And given that the inner part, the 2SAT part, works in n squared time, we get the solution which works in the time n to the power of 4, which is sufficient to pass the time limit.